Okay, apologies to everyone. We had a bit of a technical snafu, but we seem to have it worked out. So this is the session on the Venus Life Finder missions. And I'd like to introduce our speaker for the session, Professor Sarah Seeger. And just very quickly here, she's a professor at the Massachusetts Institute of Technology, and she has a whole slew of accolades, which she can go into if she likes, but I want to get right into the talk since we're a bit late. So welcome, Professor Seeger, and the floor is yours.
Thank you. I'm here to give you an update on Venus today and to talk about some missions to Venus. So this story actually starts about 2 years ago in September 2020, when I was part of a team that made an announcement that shook the world of planetary science. We announced the discovery of phosphine gas in the Venus atmosphere, and I'll come back to that. But this work involved thinking outside the box, it involved innovation, and it involved really taking risks, which is really all what exploration of planets is all about. The actual beginning of the story, the backstory, goes back a long time ago, billions of years ago, when a simple single-celled bacteria, cyanobacteria, figured out something incredibly clever: how to harness energy from our environment, namely photosynthesis, and in the process generated oxygen, a waste gas. This oxygen gas, over a long time period, maybe a billion years, eventually filled our atmosphere to 20% by volume. So here on our planet Earth, we need oxygen to breathe. Oxygen's a highly reactive gas. It shouldn't be in our atmosphere at all, unless it's being continually produced. So it's amazing, but astronomers thought of this nearly 100 years ago, that we could look for gases in atmospheres of planets far away and see if there's any gases that are outrageous, that don't belong in the context of the rest of their environment. So if there's an intelligent alien civilization with the kind of telescopes we are hoping to build, and they're looking back at Earth and they see oxygen, they'll be, wow, this oxygen shouldn't be there. It's so reactive. And they might actually be able to suspect that there's some kind of life on our planet making oxygen. So what I'm going to talk to you about is, starting out, just continuing an introduction about gases and signs of life. Then I'm going to get to phosphine and the story about phosphine on Venus and where we are today. I'm going to continue my story by sharing with you how that led me and my team to design missions to Venus that would focus on the search for signs that Venus might host life, or maybe even does host life. And I'll wrap up with some concrete mission plans. So it's not just oxygen, but it turns out that so many gases here on Earth are produced by life. It turns out that thousands of gases are produced by life. And we think of the inventory of our own atmosphere. Remarkably, every single gas present in our atmosphere, to part per trillion levels, to tiny, tiny amounts, excluding the noble gases, they're all produced by life, even though many of them have non-life dominant sources. So really, we can have so many gases, and it's not part of this talk, but I wanted you to know that my team literally works through every single molecule that can be gas at room temperature and pressure and might be considered a biosignature gas. We want to be prepared to recognize biosignature gases of any kind on exoplanets or on anything. So that leads me to talking about phosphine as a sign of life, as a biosignature gas. Phosphorus is an essential element for all life on Earth. But here on Earth, we have almost no hydrogen. And phosphorus atom doesn't want to go into phosphine, which is a phosphorus atom with 3 hydrogen atoms, but it wants to go with oxygens as phosphates. And it turns out that it's incredibly hard to make phosphine gas here on Earth. We humans make it as a pesticide, but it doesn't exist. It doesn't exist in nature. And so phosphine here on Earth is only associated with life in wetlands and oxygen-free environments, such as wetlands, in animal guts, and also it's made by humans as like pesticides. So this story continues with Professor Jane Greaves from Cardiff, UK. And she actually decided to search for signs of life on Venus, which is a way out there idea for reasons I'll get to. But in science and in engineering, as researchers, we sometimes do take sort of this privilege and joy in trying something new, something risky. So she decided to go out on a limb and search for signs of life on Venus. And to her credit, she worked through literature to search for what kinds of gases might be a suitable thing to try. And she came across phosphine in the same papers that my team came across, and found out that phosphine has a rotational transition. Molecules rotate and vibrate, and it had a ground state to first energetic state transition at millimeter wavelengths, where she is an expert radio astronomer. So she used the James Clerk Maxwell telescope. She proposed to search for phosphine gas as a sign of life on Venus. And her proposals were initially rejected, but eventually got telescope time and found support for this idea that there could be, her idea that there could be phosphine in the Venus atmosphere. Around that time, a mutual contact connected our two teams, because my team was also thinking about phosphine as a biosignature gas, and she invited us to join her team. We helped propose to use a more powerful telescope called the Atacama Large Millimeter Array, seen at the bottom of my screen. It's located at 17,000 feet in the Chilean Atacama Desert, where it's incredibly dry. And it's good for astronomy because the air is thin and the water vapor is limited there for observations. So we use this big telescope facility that has numerous dishes, radio dishes that all work together as an interferometer. It has about 60 12-meter diameter dishes. So long story short, after a number of years and a lot of data analysis, we did make an announcement of the discovery of phosphine on Venus. But first, let me go back to Venus for a moment. And why is this idea of searching for life on Venus so crazy, so out there? Well, first of all, due to a massive carbon dioxide greenhouse atmosphere, the surface of Venus is too hot for life of any kind. It is 700 Kelvin. And this is because Venus has a massive carbon dioxide greenhouse atmosphere that traps energy from our sun and keeps the surface hot. But just like here on Earth, if you hike up a mountain and it gets colder and colder, so too on Venus. When you think about the Venus surface, it's so hot, but higher and higher up, it gets cooler and cooler until about 50 kilometers above the surface, the temperature is not too hot, not too cold, but just right for life. And so for over half a century, since Carl Sagan first put this idea forward, people have thought about life on Venus, speculated rather, not about life on the surface, but life in the clouds, microbes floating around. And it turns out our own Earth has a aerial biosphere where microbes get swept up from the surface. They tend to go inside our water cloud droplets, and they stay there hanging out for, as they get swept across continental scales and eventually are rained out to the surface. But Venus, by the way, it has, like here on Earth, we don't always have clouds, depending on where you live. Clouds are fragmented, they come and go. But on Venus, the clouds are permanent. They're always there. They're horizontally 100%, they're vertically very extensive. And so this idea that maybe there are some kind of microbial type life living in the clouds. But despite having the right temperature, these clouds are still a terrible environment for life. They're very dry. The air is dry. Inside the cloud droplets, there is water, but it's locked away and not available. And the clouds are not made of water, actually. They're made of sulfuric acid, which is a very, very nasty, aggressive chemical that would destroy all of our Earth life. None of our life could survive in sulfuric acid. So that's where we're at with Venus. Sometimes we call it our sister planet. It's about the same mass and radius as Earth. It has a similar surface gravity. It turns out Venus has some interesting properties. They're not related to this idea of life on Venus, but Venus's day is longer than its year. So it's rotating very, very slowly. It's also kind of upside down. It's rotating retrograde. It must have gotten whacked by something early in its history. Here's just some information about Venus. The winds in the atmosphere are incredibly strong, 400 kilometers per hour, making the atmosphere rotate in 4 Earth days. So Venus is a really interesting planet. It's mostly carbon dioxide. This temperate cloud deck from 48 to 60 kilometers is what we're focusing on. And yeah, let's get back to this phosphine story. So we made this announcement of the detection of phosphine gas on Venus. And we're not trying to claim there's life on Venus. We're just trying to say that if there is phosphine gas, its presence is a mystery. There's either unknown chemistry, or we want to leave room for life, the presence of life making phosphine gas. Just like here on Earth, the temperatures and pressures and hydrogen content on Venus mean that it shouldn't have phosphine. It's just very, very energetically hard to make. And when we made this presentation, we worked through, or the report or the journal papers, we went through so many possibilities. We thought about volcanoes. Could volcanoes put out phosphine gas? You know, maybe, but there's very little hydrogen. Gases with hydrogen are inefficiently produced. You'd have to have a very unusual scenario, like the Venus subsurface would have to have a lot of water, too much from what we understand about Venus to supply all that hydrogen. What about meteors? You know, here on Earth, we have a lot of meteorites or dust particles from space hitting our atmosphere. Well, they could deliver phosphorus, but still phosphine would be not made in high enough quantities despite a tiny, tiny amount maybe being supplied. Lightning, surface minerals, we went through a lot of different possibilities, and none of these could match even the tiny amount of phosphine that we think is in the Venus atmosphere at a few parts per billion. So immediately when we made this announcement, and in the year and 2 years that followed, we had a very aggressive, angry response from the community. There were several complaints about this, and I wanted to just walk you through some of them so you could hear why this discovery of phosphine gas is so controversial. The first one is that when we detect a gas on another planet, we'd like to see more than one absorption feature. I was saying how phosphine rotates and vibrates. More than one. It's like as if I wanted to identify you by your fingerprints and I had like a tiny slice of one finger. You would want all 4 fingers and 1 thumb and all fully taken. But we don't have that option for phosphine. It's hard to observe from Earth. We had many people wanting to come up with a non-life explanation, and so far none of those explanations have really been satisfactory. There have been only 2 put forward. A more significant issue, and perhaps the heart of the dispute, is that all of the data that we took and that we generally take in astronomy becomes public so that other people in the community can analyze the data. And although we did a really careful job, we searched our data with the same process for absorption features at other frequencies and found no signal. We detected another line with the same procedure. Independent teams looked at the data, and some of them did not recover the signal. Because, you know, Venus, it's very bright, it's spatially resolved, and it ends up, ironically, being a challenge for our large telescope facilities, which are not meant to stare at really bright things that are moving on the sky that are spatially resolved. But more than that, the signal of phosphine is tiny, really, really, really tiny. And not, you know, when you're looking for a tiny signal and you have bright data and a lot of noise, you have to do a lot of data analysis to pull out that signal. And so some teams did not agree with our process. They did not recover the signal. Now, some teams actually did recover the signal, but wanted to argue it's not phosphine gas, it's sulfur dioxide, another gas that has the transition near the phosphine signal. So I stand by Professor Jane Greaves' continued analysis that phosphine is seen in our data. While all this is going on, Venus has seen a huge renewal of interest. People have looked at Pioneer Venus data, a spacecraft, a NASA spacecraft that went to Venus and dropped 4 probes into Venus in the late 1970s. And one of the instruments on board was a mass spectrometer. So as the probe dropped directly in the Venus atmosphere, it sucked in gases. And it took these gases and ionized them and subject them to a magnetic field. And were thus able to tell what kind of ions are in the atmosphere. So it did break up the gases into parent constituents. And this Pioneer Venus reanalysis recently shows actually some evidence for phosphine in the atmosphere. So this is ongoing. And I wanted to tell you, I wanted to just emphasize for you, well, let me tell you a bit more about, actually, let me skip that, it's a bit complicated. Let me tell you a bit more about this. I just wanted you to know, for those people who have an interest in phosphine or are following the story, I just wanted you to know that the scientific discussion about phosphine on Venus is still ongoing. And to help explain that, we made a giant table. I only have a snapshot of the top part of it here. But what we're doing is we're showing every paper put out that has a matching row and column. So along the diagonal in the gray box, we'll explain what the paper is. So Greaves 2020A, that's a discovery paper, and every paper thereafter, down, 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 what the paper is about. In the white rows, we give you a summary of the response. So let me walk you through an example here. We can take this Villanueva 2020, and that particular paper said reanalysis of the ALMA, that large telescope array in Chile data, no signal. They reanalyzed the James Clerk Maxwell telescope data. They found a signal, but attribute it to sulfur dioxide. So if you wanted to get the response from the Professor Jane Greaves et al. Team, you would go back up to the white box, response in Greaves 2020B and C. See also Greaves 2021. So you could go over here to Greaves 2020B and C and go down to where the row of the Villanueva paper is, and you'd see response from Professor Jane Greaves' team, recovery of ALMA signal using 3 different calibration methods, JCMT revisited, sulfur dioxide contamination is minimal. So of course, if you really cared about this, you'd want to go back to the actual papers and dig it out for yourself. But I only put this plot here to show you that this is a back and forth as science should be. And it will take some time to sort through phosphine. We may not resolve it until we can go back to Venus and directly sample the atmosphere for phosphine and other gases. But here it is ongoing, and there's this talk is being recorded. You can get to the spreadsheet and search through it yourself. So I'm now going to move on to tell you a bit more about Venus, because it turns out this phosphine detection, this claim detection, is not the only strange thing about Venus and about the atmosphere. And there's been this kind of growing collection of mysteries on Venus, and some of them have persisted for many decades. You know, I invite you to think about your own field of science or engineering and what mysteries might have been lingering that people shelved because it was either too complicated to explain or just needed to await more information. So here I'm showing you a cartoon of the Venus atmosphere. On the left axis, it's altitude in kilometers above the surface. And on the right side, it's showing you the temperature, which you can see how hot the surface is and how cold it gets up in the atmosphere. This temperature is in Celsius, and the pressure is in units of bar. Our Earth's surface, we have 1 bar at our surface. So you can see that the surface, Venus is not really shown here, but the pressure of 1 bar and about, it looks like 60 degrees is around 50 kilometers. And these little points here, the dots, are supposed to represent cloud particles, and schematically to represent that, to show you that there's different size cloud particles in the atmosphere of Venus. So the first anomaly that has been there for a long time is a so-called unknown ultraviolet absorber. There's something in the particles in the top of the clouds that's absorbing over half of all the ultraviolet light from our sun that falls onto the planet Venus. And that's amazing. Imagine having a mystery with no explanation. Several ideas are put forth, but we don't really know. And most of this absorption is happening pretty high up, as shown from this gray swath. However, those same particles may exist at other places in the atmosphere. So another mystery of Venus is that there are cloud particles which appear to be non-spherical, as measured by the Pioneer Venus probe in the late 1970s. What you're seeing here is a very cartoonish description that most of the cloud particles in Venus are spheres. And it's accepted that the atmosphere cloud particles are sulfuric acid, which is a liquid at these temperatures and pressures. But if the particles are not, some particles are non-spherical, they're not liquid. They have to be something else, something maybe like a sludge or a slush or something solid. And these are the so-called mode 3 particles. They're particles in the larger size, around 8 microns. Most of the particles in the Venus atmosphere are closer to 2 microns, but there is a spread. So we have those 2 anomalies. Then we have a suite of anomalies of gases that are unusual, and I'll walk you through a few of these. We already talked about phosphine. That's this orange and white. There's actually tentative detection of ammonia. And any gas with hydrogen is not expected in the Venus atmosphere, with the exception of water vapor, a little bit of water vapor. There's also a detection of oxygen by both the former Soviet Union probes that went to Venus and one of the US probes. Tiny, tiny amounts of oxygen. at around parts per million, which has no explanation of why it's there. Most robust and accepted is that in the cloud layers, water vapor and sulfur dioxide are depleted. There's a lot less of it than should be. So all those mysteries together, we actually do have an explanation for it. And it's a little too technical to get into here, so I didn't put a slide about it. I was just going to explain it vertically. But in order to explain these, you kind of have two choices. One is you can throw up your hands and say, I don't understand why we have a major depletion of, you can always, okay, I always like to say, pick your poison. There are ways to explain it, fudging your model, which is acceptable if you explain what you're doing to your model. But we actually propose a somewhat out there idea that if there's life in the Venus atmosphere, these microbes inhabiting the droplets, and they're secreting ammonia, we'll just make that assumption blindly. That would explain why there's ammonia in the atmosphere. I want you to know that in our stomachs, there are bacteria that secrete ammonia to help neutralize the acid. So interestingly, if there's ammonia, this would help neutralize the droplets. And then the sulfuric acid droplets, instead of being orders of magnitude more acidic than the most acidic environments on Earth where life is found, these droplets would now be comparable, still acidic, but at a level that at least Earth life could inhabit. Now, this ammonia, I just made that assumption out of the blue, but it's interesting that if life on Venus is making ammonia, the most energetically efficient, like the lowest energy way to make ammonia, still requires energy, also produces oxygen as a byproduct. So we can explain the presence of oxygen gas. Now, if there's ammonia neutralizing the sulfuric acid, slightly neutralizing it, it sets off a chemical reaction that sucks in sulfur dioxide and water, thus explaining the depletion of sulfur dioxide and water in the clouds. So one of the mysteries of Venus, I put on the far left here, emerging research on Venus's sulfuric acid. We could imagine that there is Earth-like biochemistry, there is somewhat Earth-like life in the droplets, but this life would have to be manipulating the environment, making the sulfuric acid less acidic, and by emitting ammonia and setting off this cascade of reactions that explains a lot of the anomalies on Venus, including, by the way, the ammonia would go through a reaction to make a kind of ammonia salt slurry, making the droplets non-spherical. I'm not sure if that made too much sense the way I described it. We do have a paper with the reference down there that you can look up and read the details. But now I'm going to pause for a moment, because the most important thing, or the single most exciting thing I can actually tell you right now, it's not published, I don't have details, I just have it on the right side here. And if there's only one thing you can ever remember or take away on this talk, it is about sulfuric acid being a really shockingly dynamic and interesting chemical environment. As planetary scientists and learning about Venus, we're brought into this paradigm that sulfuric acid is sterile to any interesting chemistry. And we're learning that's not the case at all. Jan Spacek and Steve Benner, it turns out, they have studied sulfuric acid in the lab, seeding it with small organic molecules. And they found that it ends up being a rich organic chemistry. They put like a small molecule and watched it evolve. And they looked a little more into this in the literature, and they discovered that this is already known in other industries. They've discovered that this actually is already known in other industry. In the oil refinement industry, they actually know about this because they use concentrated sulfuric acid to catalyze reactions to move crude oil to more sophisticated forms. And it's not just in the oil industry, it's other areas of chemistry. We have another colleague that we've inspired to work on this, Daniel Djustjevic at Harvard. And what he's done is taken lipids, certain fats, specially chosen, put them in sulfuric acid, and shown they can form a spherical vesicle. This is a group that's trying to develop life from scratch on Earth. And wow, imagine that some fats are not only sulfuric acid resistant, but can form something that I like to think of it like a cell membrane. It's definitely not a cell membrane because its permeability and things like that aren't studied. But I just wanted you to know about new emerging research on Venus's sulfuric acid. So all of this was part of an effort and motivates this idea to go back to Venus, to study astrobiology, to check out habitability, to look for rich organic chemistry in the cloud droplets. And I want you to know that during the whole phosphine and during, I assembled a team to study Venus, completely separate to us. NASA decided to accept 2 mission proposals to go back to Venus, and the European Space Agency did so as well. And they are going back to Venus towards the end of this decade, but they're not studying astrobiology and they're not interrogating the cloud particles in any way. And I do want you to know that there's a big resistance to talking about life, Venus, and missions in the same sentence. We found that lots of different people, not only from government agencies, are highly, highly resistant to this. Sometimes I think that means it's a great idea to like be pushing the envelope, but people are just conservative. So you can read our 120-page study at venuscloudlife.com. You can get our report about all the ways we could go to Venus. We came up with 3 missions, and that's what I'll be talking about for the rest of my talk. That's related to what we want to do to go back to Venus. And we have 3 mission ideas. We call them small, medium, and large, or like short-term, medium-term, and long-term. And let me walk you through some of them. Our first mission under the small, short-term category, we call this the Rocket Lab mission to Venus. And this mission has a target launch date of 2023, followed by a backup launch date of 2025. So the target launch date is May 2023, backup is January 2025. And this would be a Rocket Lab mission where Rocket Lab will launch an Electron rocket with a Photon spacecraft, and the spacecraft will cruise to Venus. And inside Photon will be a probe, a small probe measuring about 40 centimeters in diameter. And this probe will just drop into Venus. It will be going super fast with high Gs, and the probe won't have a parachute. This is like a low budget mission. We have room for 1 single instrument in this probe. And I was responsible for choosing for the team that chose the instrument, for the science team and the science instrument. Obviously, I skipped a whole lot there because a lot has to happen to get a mission and to get the team. And we have had a crazy couple of years. We chose an instrument. We called the autofluorescence nephelometer. Okay, we only had less than 1 kilogram for our payload. And what this autofluorescent nephelometer is going to do is it's going to shine a light through 2 windows. One window is in the pressure vessel, which is inside the probe, and the other window is on the probe. It'll shine an ultraviolet laser out through the windows to the cloud particles, searching for autofluorescence. So if you think of what autofluorescence is, if you think of like a nightclub you might have been to, or a child's like fun house, when you shine the ultraviolet light and then it lights up like blue, that's the ultraviolet high energy photons are exciting an electron that is dropping back to its nascent energy state. And if there's interesting chemistry, if there are organic molecules inside these cloud particles, especially ringed molecules where the electrons are delocalized and easy to excite, we'll be able to, confirm this idea that the sulfuric acid droplets have interesting chemistry. We're not finding life here, okay? We're just looking for organic molecules. Life needs organic molecules, so it is a step in the right direction. In addition, we'll be measuring the backscattered polarized radiation from the droplets. This was already done before in the Pioneer Venus mission in the late 1970s, and we'll be constraining what the particle's index of refraction is and size and somewhat shape so that we can try to learn more about the cloud particles, these mode 3 cloud particles that I explained the mystery of, that they're not spherical and they're made, we want to know what they're made of. This mission is very short. Remember, it's a low-cost mission. There's no parachute. Here's our profile in the Venus atmosphere. On the left, you're seeing altitude in kilometers and also temperature. And on the bottom, you're seeing time from entry in seconds. So you want to look at this black line here, showing you entry at 200 kilometers, 11 kilometers per second, and it's kind of rapidly going down. We care about the cloud layers, and we're only planning to take data while we're in these cloud layers with our science instrument. That lasts for about 5 minutes. Our probe will have a direct relay to Earth. We don't have any comms relay, communication relay. We're going to send our data direct back to Earth. And we'll continue to send data as long as we can. But this atmosphere in Venus gets really, really hot below the clouds. And so at some point, our electronics will stop working. At lower altitudes, the pressure is very high. Our pressure vessel might explode. And if any of that doesn't happen, we'll crash land at the surface. We're not planning to take data beneath the clouds. So that's our first mission. We're really excited about it. Here's a picture of the pressure vessel, and we have 2 scientific articles on this that are now published. This is showing you the probe. And on the right here, it's just a schematic trying to show you a few things about the probe and our instrument. This black rectangle here is our autofluorescence nephelometer, AFM. And this shows you it's going to be looking out of 2 windows and interrogating the clouds outside of the probe. It's supposed to be away from the airflow off this heat shield and off of the probe so we don't get contamination. Inside there's batteries, and there's a few other things shown in this figure. So I'm now going to move on to our second mission concept. Unlike the first one, we don't have an actual mission. We don't have money. We're still making plans for what this mission would be and how we'll get it off the ground. I am a professor at MIT, so we call this an MIT-led international consortium. We have a lot of partners all around the world. If you're interested in Venus, please reach out to me. This medium mission, we do have 2 different concepts. One is a larger probe with a parachute that could spend 1 hour in the clouds taking data. Another concept is a balloon mission, and that's what this slide is showing you. You can see here, it's showing you entry on the left here at 180 kilometer altitude above the surface at an 11 kilometers per second velocity. Then a drogue chute deploys to slow down the entry vehicle. The heat shield gets jettisoned and the back shell separates. And then the balloon system is free and has to do its thing. To me, this is like the, kind of the most scary part of the mission. So the balloon has to inflate and before it can do science operations. In this so-called medium mission, we have a lot of different ideas for instruments. What I would love to see on this balloon personally is a mass spectrometer so that we could identify what chemicals are inside the cloud droplets. If we really do believe there's a complex organic chemistry going on, wow, wouldn't it be amazing for us to learn like how complex is complex? And could we associate any of these molecules with some kind of biochemistry? Are they the right complexity for that? That would be my personal goal. This balloon, it could last for a week or 2 or more. It's worth emphasizing that the former Soviet Union sent 2 balloons to Venus in the early 1980s, the Vega balloons, and they lasted each for 2 days. They carried all their own batteries, and it was amazing feat of engineering. So we would send our balloon. We imagine having a fixed altitude balloon. We've had some ideas about deploying mini probes so that we could also probe beneath our fixed altitude. But this idea is really still TBD. We do have a set of things we'd like to measure. We want to determine how much water vapor is in the cloud layers. We really need to know how acidic are these cloud droplets, because the theory I tried to explain to you, how maybe there's some life in the droplets, making them less acidic, like neutralizing their environment so they can survive. We'd like to measure that. We'd like to search for metals in the cloud particles. Metals are needed for all life as we know it to catalyze reactions. We want to, of course, measure the temperature, pressure, and wind speed. In terms of our search for evidence of life, we'd like to search for gases, such as ammonia, perhaps phosphine, methane, and other reduced and anomalous molecules as signs of life. Then we want to go back to this idea that there's organic material in the cloud layer particles and identify what that is. Finally, in doing all of the above, we'd like to know if the cloud particles are liquid or solid or both, and to understand if the clouds are homogeneous. Because our third mission concept, remember I was doing small, short-term, medium, midterm, and large, complex mission long-term. It leads me to the third mission in the series, which is not funded, although we have funding from NASA under the NIAC program to study this, and that is the sample return idea. And the last part of my talk, I'll just spend a few minutes talking to you about this concept and what work we've decided to focus on. So in this idea, it's a massive endeavor where we would start again by entry of an entry vehicle and deceleration with this drogue chute that deploys to slow everything down. This time we also have a balloon that inflates, and the balloon inflation system gets jettisoned. But what's different about this from the one I just talked about in our so-called medium mission is we want to do a sample collection and return that sample to Earth. So this whole system needs to have like a giant balloon with a rocket attached to it. Well, I'll say little rocket, but okay, it's still pretty massive. And I have some actual numbers for you a bit later. And this balloon could last, it doesn't need to stay there that long. Just a few days is honestly enough to collect what we need. We want to collect some gas. We want to collect up to an order grams of cloud particles, liquid and solid. And this would be incredibly challenging to, the Venus atmosphere. Remember, the winds are really strong. There's turbulence. We have to point this rocket towards the orbiter, and this rocket would launch. We'd actually move the balloon up to a higher altitude so the rocket can launch more easily, would rendezvous with its orbiter, and the orbiter would return to Earth. Now, if you're at this session, you're probably a fan of or know about the planned Mars sample return mission. So in this concept, we're relying on parts of the hard problems to be solved for other missions. So why do we want to do this? We want to enable robust detection of life. Most of the ideas we have to go to Venus and look for life, they're not as robust as bringing a sample back to Earth to study in very sophisticated laboratory analysis environments. Okay, I already showed you an atmosphere sample return concept of operation. So what we decided to do in the phase 1 of our NASA grant is to focus on some concepts that need maturing. How to capture solid and liquid particles. We wanted to address our Venus ascent vehicle. How massive did that need to be so we can talk about the aerial platform and see if the whole thing closes, if it's possible at all. So in terms of solid particle capture, we're working with Honeybee Robotics. We'd like to capture particles down to 0.2 microns. The goal is to have these particles come through this collection zone. We can have a little fan blowing particles in. We'd probably want to heat them to get rid of the sulfuric acid. So we're left with whatever hope for solid materials inside the particles. The solid particles would land on this gold sticky tape. And there's just this spooling system that would spool and capture that tape and roll it all up and package it for, close it all off so it can be sent back to storage to get back to Earth. So this sticky tape spool mechanism is one of the things that we're pushing forward. In terms of liquids, we're not as far along. We have looked at what people do here on Earth for liquid. There's passive collectors, like here's a little picture of a little fog harp. Actually, people have giant fog harps in some places in the world to collect fog for water. But the idea is that the liquid attaches itself to metal wires and it drops down due to gravity and then gets collected at the bottom. There's also active collectors, and you see one on the right here. People put these outside and they suck in tons and tons of liquid. That's probably not the direction we're going, but it's certainly on here. Okay, in terms of our aerial platform, by the way, this study is not too detailed. In the NASA NIAC, there's different phases. We're in phase 1. If we get selected for phase 2, we'll do more detail. Phase 1 is kind of like a proof of concept. This is showing, so for our aerial platform, we'd have a super pressure balloon that could lift up to a 2-ton gondola. We'd have a controlled descent from 48 up to 64 kilometers where we would deploy, or where we would launch our rocket. This plot is to sort of try to get our heads around how much mass and how the mass depends on launch altitude. You can see on the left, it's gondola total allowable mass in kilograms. So going from 0 in 1,000 intervals up to 7,000 kilograms. The bottom is balloon volume. If you know anything about balloons, these are big volumes. And the different curves are for different altitudes. So it's really just showing you that if we can launch from a higher altitude, we can accommodate more mass. So finally, about our Venus ascent vehicle. So oddly enough, here on Earth, there's some commercial companies, including one called Rockoon, who want to launch rocket from balloons. So this idea is not without precedent. But in this case, we aim to transfer our sample to a 300-kilometer orbit. We're thinking about a 2-stage solid propellant. And I already mentioned how the attitude, determination, and navigation will be challenging in the Venus clouds. So this slide is more just to let you know that we're working on it. So now I'm going to get to the mission, motivation, and summary. These are your takeaways from my talk today. So Venus has many long-standing mysteries. Some are measured directly in the atmosphere by probes from nearly 40 years ago, from when NASA sent 4 probes and the former Soviet Union sent like over 12 probes directly in the atmosphere of Venus. We're interested in many different gases: ammonia, water vapor, this depletion of sulfur dioxide and water vapor in the cloud layer, reestablishing the presence of oxygen and perhaps phosphine, as well as getting to the heart of what the large non-spherical particles are actually made of in the Venus atmosphere. This whole phosphine story, I spent some time trying to explain it all to you, but a lot of the thrust forward for Venus today, it's not related to phosphine. It was initiated by phosphine, but there's so many wonderful things going on. Phosphine motivated a flurry of new activity, of old data, new models, and a fresh look at chemistry. There are missions from NASA and ESA going to Venus. I focused on my team's missions, which are a series of astrobiology missions to try to understand the habitability and possibly existence of life on Venus. Thank you so much for your attention. That ends my talk.
Okay, well, thank you very much, Dr. Seeger. So did you see those questions that were from Huva in the chat box?
I do, yes,
read them.
I can.
Okay, did you want to address those first? I want to make sure the
Yes.
attendees get their due.
Some questions. Will camera telemetry be available for viewing on this mission, the Rocket Lab mission to Venus, notwithstanding transmission delays and bandwidth issues? Sadly, we decided not to have a camera. We won't be taking any images. When you transmit direct to Earth, there's such little data, like we just don't have the data to do that, unfortunately. Okay, the next question. If Venus rotates so slowly, this would contribute to the severely high temperatures on the day side. What is the average temperature on the night side? What's amazing about Venus is, surprisingly, the temperature is basically the same all around the planet, but different for different altitudes. So the surface temperature of Venus is the same all around the planet. You know, at higher altitudes, it's the same all around. And this is maybe counterintuitive, but if you live somewhere cold, think about this, like on a really cold day in winter, you open your front door of your, if you have a house or you live in, the ground floor or the lobby of your building, and the hot air rushes in and the cold air rushes out. And that's kind of what's happening on Venus. The air is getting whipped around really fast and it redistributes that heat so thoroughly that these temperatures are not, you don't have those day and night temperatures like you'd expect. Okay, those are all the questions in the chat.
Yeah, I believe that finishes the chat box. I just had one quick question, if you don't mind, regarding the signal to noise for your detection for phosphine. Do you have a rough number for that? I was just curious.
Our detection is around 10, signal noise around 10.
That's pretty good.
Yeah, it's a good signal to noise.
Yeah.
So the question, but the signal itself is pretty tiny. It's like a part in 10,000. So it's not so much the signal looks low, it's how you get to the signal that's being questioned.
Yes, I see. Okay. Very good. And then I guess I don't see further questions, but one more. Do you see these missions you have planned adjusting where they're looking for life on Earth in terms of a high sulfuric acid environment? You say that's there's a certain molarity that is not conducive to life on Earth, but would they readjust? Okay, looking for life on Earth and different environments.
That's a great question, actually. I just really love that question. I don't know off the top of my head if there are any more acidic environments on Earth than the most acidic ones looked at so far. When we think of the acidity scale, pH, there's like 0, you can even go below 0, and 0-ish has extremophiles, but I'm not sure if we have environments that exist without that, but that's like a great question, actually. People have always wanted to find what they call a shadow biosphere. Is there life on Earth that's actually different from our life, that doesn't share our DNA because it can't? And so that's that your question actually really ties into this other idea. So I'll have to put that on the list of things to look into.
Yeah, I think it's such an amazing feedback, right? You're looking at Venus to find out more information about our own planet. That's an amazing thing. Okay, well, I don't see much more in the chat box.
There's one more question I'll put in the chat box.
Oh, okay. Thank you, Tinsley.
If the reason for these anomalies is due to life, can it be reasonably assumed that it is independent from life on Earth, i.e. Venus did not come from Earth's life? I would have to say yes to that, because the environment is so different from anything on Earth. Like if you took a cell or an ant, which someone on my team did, and put it in sulfuric acid, it would literally get destroyed in like the blink of an eye. So our life, if it got sent to Venus right now, there's just no way that it could survive at all. If there is life that secretes ammonia and makes its environment less acidic and better for it, that has to be something that evolved over a very long period of time. However, many people believe that Venus had water oceans, maybe even up until 800 or 900 million years ago. And so if it did have oceans for a really long time, it is possible that, life from Earth went to Venus. And that over time, as Venus went into a runaway greenhouse and the oceans evaporated, that life had to migrate to the clouds and evolve. So I guess there's still a small chance that might have happened that way, but I really think that's not. I really do think if we find it, it can be reasonably assumed it's independent. Great question.
Okay, well, I think that, oh, sorry, there's one more that just popped up. Did you see that, Dr. Seeger?
I do, yeah.
Okay, I'll leave you to it.
Oh, is there a working concept of heat exchange as part of the engine or drivers to keep the tech temperature capable while it functions? Well, what we have right now is we do have a pressure vessel inside the probe. So the instruments are inside like a protected area where they're not really going to be kept cool, because this mission is not lasting very long. And the mission is operating in the cloud layers where the temperatures are not very different from what we have here on Earth. So in that sense, we don't have any heat exchange, and we have some passive cooling, because any instrument like your computer, it's really hot, right? Like right now, if I touch the bottom of my computer, it's really hot. We do have a way to passively cool our instrument, because when we're operating it, the power is hot. We want to get rid of that. But we're not doing that. When it gets so hot, too hot for like electronics to work, we just simply don't operate there, and we don't care that much about that environment. That said, there's like a whole other industry of people who want to find ways to have electronics work at very high temperatures. But I'm not sure what mechanics they have to keep the tech temperature capable while it functions. So this answer is we're operating in relatively benign temperature environments, and we also have a pressure vessel.
Okay, I don't see any more questions popping up. Oh, just another comment. So, okay. Well, I would like to thank you so much, Professor Seeger. Your talk was fascinating. I found it so much so that I'm going to go read more into it.
Great. We'll reach out if you have any follow-up.
Yeah, thank you very much for your time. Take care. And again, amazing talk. Thank you.
Thank you. Bye.